Thank you very much, and I'm absolutely delighted to be here today to talk to you about mathematically modelling the world around us from smoothies to the stars. So just before I begin, I got a brilliant introduction there, but a little bit about me. I am from Belfast in Ireland. I studied my undergraduate in pure maths at Trinity College Dublin before undertaking my PhD in applied mathematics at the University of Oxford. For the last 3 years, I've been working as a research scientist at NASA Ames, and I'm also the co-founder of Mathematicals, which has been explained to be an outreach initiative aimed to encourage more girls to consider careers in mathematics, but also just to make maths more accessible, more fun, and showcase all of the different ways it impacts our lives. And if this conference and this session isn't a perfect example of many of those ways, I don't know what is. So we've heard a lot of mathematical models so far. We've already got a really fascinating insight into the different areas where maths is critically important. But just strip it all the way back. What is mathematical modelling in itself? Well, models in general, models that you'll have come across, be it model trains, model airplanes, or even those little tiny versions of your city that you might see in a museum or a tourist centre. Models help us understand complex systems. Things that are big or difficult or far away or anything that just is a bit beyond our reach. We can use models to simplify that and get information and knowledge and build up our understanding. So this middle image that you can see, this is a model of the space shuttle within the wind tunnels at NASA, where the engineers were testing out how the space shuttle would cope in the extreme environments that it would be subject to when it tried to get into space. So mathematical or models are so important to test things out before we start going to the real thing. It's cheaper. You can change things easier. You can really test what's going to happen before you throw your millions of dollars of funding into the big mission. And then mathematical models, as we've heard, simplify that even further, because we can begin to understand complex systems on a computer or even on a piece of paper. So even cheaper, even quicker, and you've got far more control of your environment, your parameters. You can make so many more tweaks. And mathematical models can be self-sufficient. They can be enough. That could be all we need to make decisions. Or it can be the first step before we start to develop physical models, before we start to develop the final product. And why do we care? Well, there's so many areas of mathematical modelling that are important, and we've heard about a lot of them so far. And when I came to write this talk, I found it really difficult. Not because I didn't know what to say, but because there was just too much to cover in 15 minutes. So I'm going to just touch on 3 important areas of mathematical modelling, the first of which is for prediction. So we've already heard a lot about climate and about weather. So every time you open the weather app on your phone, you're looking at the output of a mathematical model to help us understand, is it going to be sunny on Saturday or can I plan that picnic? We're also very familiar with the use of mathematical models to understand the spread of disease. During the height of the COVID-19 pandemic, we were constantly being bombarded with this is the next peak and this is how many deaths we expect. But not only was mathematical modelling important to understand the number of cases and to predict how many people might become infected, but it was also used to try and understand how does the disease, the airborne particles, actually propagate from person to person, and how might an infected person end up passing on the disease. So it allowed scientists to inform us how far apart we should stand in order to try and mitigate transmission. Number 2 is discovery. So we've talked about having the space shuttle test in wind tunnels. And if you've got access to that, that's brilliant. If you can take something, generate data, have samples, that can be extremely important. But what happens if your system is too hot, too far away, too difficult to take samples? In that case, we rely very heavily on models. And that is the case for trying to understand what planets are made of, exoplanets. They're so far away, we can't go there, we can't sample the atmosphere, we can't look at the soil. So we rely heavily on the data we're getting back from telescopes and from mathematical models to help us understand that data and predict what we think the planet might be made of. Similarly, for drug discovery, we can't really see firsthand necessarily how a drug is interacting with cells within the body, like we also heard. So models can be extremely important to try and see how a drug might try and treat a disease before we start testing this on humans. And finally, optimization, which might be one of the most important areas for industrial mathematics. How to make things better, faster, stronger. All of these things can be helped with the use of mathematical models. So every time you get a new iPhone, your battery lasts a bit longer. There is a massive area of mathematics dedicated to battery modeling as we try to move towards a carbon zero future, as we try to eliminate the use of fossil fuels. We're becoming more and more dependent on batteries. So there's a huge push to try and improve our batteries, and mathematical modeling is at the core of that. Just making cars go faster, Formula One, aerodynamics, that's all coming down to mathematics. Mathematics is at the core of all of these things. And I'm just going to pause on optimization for a moment because I mentioned I did my PhD at Oxford. The course itself was called Industrially Focused Mathematical Modelling. And what happened was companies and industries would come to us with a problem that they had in their industry that they wanted mathematics to solve, to help them get to the bottom of their problem. So the first ever research project I worked on as a PhD student was from a company called SharkNinja. You might know their Hoovers or their air wrap dupes, or maybe their blenders. And it was the blender part of the company that I was working with. And they asked, how do we make our smoothies smooth, but keep our blenders quiet? So what they were finding was they were getting these brilliant smoothies. They're so smooth. The blender was doing its job, but it was very, very noisy. And that was the biggest customer complaint, was that they got a great smoothie, but they almost didn't want to turn it on because it was so noisy. So SharkNinja came to Oxford. They said, how can we solve this problem? Can mathematics help me get to the bottom of this? So where do you start? How can you begin to figure out how to get a smoothie smooth and keep it quiet? So the trick is to start with the simplest possible model. In all of the cases that we've talked about today, the starting point is as simple as you can make it. So that's what we did. So I want you to imagine putting a carrot into a blender. That's it. What happens? You turn the blender on, the blades start to spin, the carrot might get chopped. And as it spins and it keeps going, it gets chopped some more, until eventually you'll end up with lots of smaller pieces of carrot of lots of different sizes. But depending on how you chop, how long you chop for, the type of blade you use, you'll end up with different sizes and different numbers of sizes, different numbers of pieces of carrot. So you could have only a couple of big pieces and lots of small pieces, which is sort of what you want. Or you could have a big chunky smoothie with loads of big pieces and only a few small pieces. So that's the essence of the problem. That's the core of the simple model. But how do you actually turn this into a mathematical model? Well, our approach was to just keep track of the number of pieces of each size. Okay, so I mentioned there's lots of different sizes, so all we're going to try and do is count the number of pieces of every size. So what I mean by that is, let's imagine we're trying to keep track of pieces of this size. So we're starting with 6. What happens when we turn the blender on? The blades go round. Some of these pieces are going to get chopped to become smaller pieces. So they're no longer the pieces we're interested in. They're gone. So we might only have 4 left. But what will also happen is there'll be bigger pieces in the blender that as the blades spin, they also get chopped and they might form pieces of the size we care about. So we gain some pieces from this. So formulating this somewhat mathematically, we can think about this as the number of pieces of the size we care about after a chop is equal to the number of pieces before the chop take away or subtract any pieces that got chopped and became smaller, but add on any pieces that were created by having larger particles that got chopped down. Okay? So this is it, really. This is the model. That's as simple as it is. And we've formulated something without even really using any numbers. The only mathematical things we've got in there is a plus and a minus sign. But if you understand this, you understand the model. And you can obviously start to add things in, but this is really the core. So, of course, we did formulate this a bit more mathematically and introduce some more mathematical symbols. But this was the essence. Does it work? So this is a graph given to us by the company. So they had some fancy lasers and things that were able to measure the diameter or the size of the carrot pieces and how much carrot corresponded to that size. So you see, oops, okay, spoiler, that's my model. So the size piece is along the x-axis, and then the volume of pieces is like the amount of carrot corresponding to that piece. And then this second graph is the output of our model. So you can already see we're capturing the shape really well. We're even getting our peak at about the right size and about the right height. And I just really want to emphasize how simple this model was. It was only thinking about chopping. We weren't thinking about fluid dynamics. We didn't have any juice in there. We weren't thinking about the mixing or the shape of the vessel. All of those things were omitted from our initial assumptions. So what I'm trying to say is that you can make a lot of progress. You can get pretty insightful results from the simplest of cases. And then once you've got that foundation, once you've got that starting point, you can start to add more things in, make it more complex, and start to think about more complicated situations. Which brings me to exoplanets and trying to understand what they're made of. So some of you might be familiar with how scientists understand what a planet is made of. It's through a process called spectroscopy. And essentially that's just looking at the data that we get back from the telescope is called an electromagnetic spectra. And the spectrum is all of the wavelengths of light, so kind of just like a rainbow where you have visible light broken up into all its colors. You can do that for the whole electromagnetic spectrum. So from gamma rays to radio waves, you can break that up into all the different wavelengths and look at the intensity of every wavelength, or the brightness, how much of each wavelength is being detected by the telescope from that planet. And you get this squiggly line, and the squiggly line is the spectrum. And from the different peaks and the different features of this squiggly line, we can infer what chemicals might be in that planet, whether there's water, fingers crossed, or carbon dioxide or nitrogen. You can get a lot of information from this spectrum. And we need mathematical models to help not only predict spectrums from what we know and see if we get what we expect, but also to understand the spectrums that we're getting from the planets. It was mentioned, I think, by Karen that a lot of the data that we get from complex systems can be sparse or noisy. So you really do need those models to kind of get any interesting or relevant information. So I don't think I have too much time left, but I'm just going to go through a really brief overview of one of the models that I worked on during my first year at NASA, which was to understand clouds in atmospheres. So just like when you look outside and you see white fluffy clouds in the sky, those are going to impact how planet Earth looks from far away. So if anybody was looking at our spectrum from light years away, those clouds would be really important to understand what the planet's made of. And there's clouds in exoplanets too. In fact, there's even more problematic clouds than our own. So it's really important to understand these clouds to feed into our bigger atmospheric models. And this particular model is called Virga. It's an open source model, so everyone can go download it, play with it. There's some really nice tutorials to make it user-friendly. And I've kind of broken it down into some main components. So we start with our assumptions and our inputs, which you would do for every model. And just like with our blender, where we didn't worry about fluid dynamics, we didn't worry about mixing, We also, in this model, omit microphysics, so how cloud particles interact on a very small scale. We don't worry about that too much. The only microphysical process we care about in this particular model is condensation, and it's very heavily simplified. We also have pressure temperature profiles and input, so the sort of temperature of the planet and different characteristics of the planet. These parameters, this eddy diffusion coefficient, how it mixes, sedimentation efficiency, how it rains, different things that we put into the model. And then the guts of the model is this middle section. And this is where the mathematical equations would be. But essentially what we're doing, what we're solving is, at first, we're balancing an upward turbulent mixing of cloud particles, so as they rise, and balancing that against downward sedimentation, so as the particles turn back into liquid and rain out. Once we've got that balance, we also have to come up with the particle size distribution. So really similar to what we just did with blenders, we want to know how much of the cloud is attributed to each particle size, because the size of the cloud particles, the size of that condensate matter, is extremely important in understanding how the clouds will scatter light. And then the output of the model, we get our cloud profile, which we've simplified into sort of 3 main parameters. And those parameters are what we would then put into a larger radiative transfer code to understand how the atmosphere, along with the clouds, would scatter light and produce a spectra. So I think I'll probably out of time. So thank you very much for listening. If you're interested in learning more about mathematicals and the kind of work we're trying to do to encourage more young people to pursue careers in maths, please check out mathematicals.com or mathematicals on Instagram. Thank you.